Okay, today we're going to look at, this is really so you see here I have Newton's second law. I didn't write the net force there, but basically Newton's second law of force equals mass times acceleration. There is, this is just for forces in general. There are many, many kinds of forces, although when it comes down to it in physics, there are four sort of fundamental forces that we know about. That's gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. We're really just going to talk about gravity right now. The electromagnetic force, you may think, well, that has to do with probably electricity or something, and it does, but it's actually one that you experience a lot because it turns out that everything is made out of particles that have a charge, right? Atoms have a positively, usually at least, have a positively charged nucleus, and they have that negative charge, electrons around. So actually when you press things and when you push things and when you stand up on the floor, there's a lot of electromagnetic force that's there. But for right now, I want to focus on gravity. So gravity, in the biggest sense, gravity is simply this fact that matter is attracted to other matter, right? So when you have things that are made out of matter, things that have mass, they they're attracted to each other. They pull towards each other. Now, we think of gravity, because obviously it keeps us on the ground, or keeps us from, a lot of times people think it keeps us from floating around or something like that. And gravity certainly does that, but gravity is a force between any two objects that have mass, right? So, this little pen and this calculator, right? They both have mass, and they're actually pulling towards each other. But gravity as a force is incredibly weak. At least in small amounts. So, the amount of gravitational force between these two objects is essentially negligible. You could calculate it, and it would be an incredibly small force. But when you have something that's big enough, like a planet, then gravity starts to become more important. So right now there is, gravity is pulling everything down. The whole Earth's mass is pulling down on something, and so that's why, if I let go of my pencil, it's going to drop because gravity, Earth's mass is attracted to this mass and it pulls it downward. Likewise, actually, Likewise, the pencil actually pulls up on the Earth as well, but because the Earth has so much mass and has so much inertia, that doesn't really matter, or it doesn't affect it. So, gravity is going to pull stuff down, and it pulls the other way. Big picture is that we think of gravity. You might think of it as being like a force that's strong because you're aware of it, and you know all that, But gravity is actually incredibly weak, right? I mean, again, think about the entire Earth, this massive, massive place that not even your whole lifetime will you be able to see it all, is pulling down, on this calculator, and I can just toss it up in the air, no problem. I can overcome the entire Earth's gravitational field as a simple, person. So anyways, all that is to say, gravity is one of our four fundamental forces, probably the one we know best, we're most familiar with. It's actually one of the weakest. Now, when it comes to weakest and strongest, it does matter about the scale, the size scale. Gravity is sort of the dominating force over large distances. But, all right. Anyways, all that is to say, we can rewrite this equation, right? So this is Newton's second law here. We can rewrite this equation. If we're going to talk about gravity, right, the force that we associate with gravity, the force of something pulling down, we call that your weight. So I'm just going to use W there for weight. So weight is going to be, the mass is still important here. The only difference here is that the acceleration, instead of a generic acceleration, right, we have an acceleration due to gravity is what we call it, and that's G. So this is our weight equation, and it is very similar. It's very similar to the equation that we have for Newton's second law. It's just more specific because weight is a specific force. So the weight of an object is going to be equal to its mass times the acceleration due to gravity. Now, later on, we're actually going to study gravity using another equation that is a little bit more I don't want to say better, but it's more descriptive than this right here, because this thing right here, G, is dependent. I mean, how do we figure out what G is? Well, it's dependent on what else is there. So on Earth it's going to be some number. On Jupiter it's going to be some number. But there is a equation which has a little bit more detail to it that can help you figure out exactly what's going on. But suffice it to say that we can figure out what G is for any planet or any area, and it's going to change. And even on Earth it changes. Technically there is less gravitational force. If you go up like on a mountain, you are further away from Earth's center of gravity, so your weight decreases. Likewise, if you go down into a valley, you're closer to Earth's center of gravity, and your weight increases to a certain point at least. So even on Earth, the gravity is going to fluctuate some small amount. But big picture, this is the equation here: weight is mass times gravity. And again, you have that in the slides that I provided, so this shall not be new to you there. Okay, well, let's look at what is the difference between weight and mass, okay? Because these are two terms that we may think are the same, right? What is weight versus mass? So weight has to do with gravity. Weight is the amount gravity pulls on you. It's really the amount of gravitational force on you, or any object really. So when we talk about astronauts going into space, you may think that there is no, you may have heard, well, you're weightless in space or whatever. And that has to do with this concept called free fall, which I'm not going to get into right now, but there is actually a weight force there. But again, there's no apparent weight because they're falling. But the point I'm making here is that, your weight is a gravitational pull on you. And so if you were in the middle of space, like empty space, pure empty space, where nothing was around you, then you would have no weight. Nothing would be pulling you down. If you went to, let's say, the surface of a planet like Mercury, you would have less weight than you would on Earth, because Mercury has less mass, less stuff pulling on you, so you have a smaller weight force. But mass is different. Mass is just is how much matter, or you could use the word stuff there, matter's a little better, how much matter you are made of. So weight has to do with the gravitational force on you. Mass is just how much stuff you're made of, how much matter you're made of. And there's a relationship between the two, right? But they're not the same thing, right? In other words, if you were to go to a different place like Pluto or Jupiter, your weight would change drastically. But your mass, the amount of stuff you're made of, that wouldn't change. Your mass would still be the same. Mass is usually measured, the standard is kilograms, and weight, the standard here is going to be newtons. So when we look at this question here, since the box has a mass of 80 kilograms on Earth, what is the mass of the box on Jupiter, where G equals 26.0 meters per second squared? So I know some people were confused about this because they say, well, I know what to do, right? We're going to apply the weight equation that we just used, W equals mg. So I'm going to take the mass and multiply it by G. And certainly if you did 80 times 26, you will find the weight of that box. But notice this, and if you did it 80 times 26, you get, sorry, I typed it in wrong. 80 times 26, you get 2,080. So 2,080 newtons would be how much this is, which is obviously a lot. Newtons, that would be the weight. But the mass doesn't change. So if the box has a mass of 80 kilograms, right, and it says what is the mass, guess what? The mass on Jupiter is still going to be 80 kilograms. So don't let that question trip you up. There's a couple like that on the practice. If it's asking for mass, the mass never changes. So the mass on Earth was 80 kilograms. The mass on Jupiter would be 80 kilograms. The mass on Pluto would be 80 kilograms. The mass in an empty vacuum of space where there's no matter around you would still be 80 kilograms. Because again, mass is just a measure of how much stuff you are made of. Let's look at another example where we're calculating weight. A box has a mass of 20 kilograms. What is the weight of the box on the moon where g equals 1.6 meters per second squared. Okay, this is simple enough, right? This is just a basic, because it's asking what is the weight, so we just use the weight equation. So the weight is going to be mass times gravity. So in this case, the mass is 20 kilograms times 1.6 meters per second squared. So weight is going to be simply 20 times 1.6, which is 32. Newtons would be the unit there. Remember, Newton is our unit of force. And technically here, right, this is, if I wrote it out better, it's 20 kilograms times 1.6 meters per second squared. So really it would be 32 kilogram meter per second squared. But as I discussed on Tuesday, we have a nickname for this. Instead of saying kilogram meter per second squared every time, we just call that a newton. So that's 32 newtons. Okay, so you can see this is pretty straightforward, pretty easy. I could ask you for one of the others. Like I could ask you what is the mass if you know the weight, or I could ask you what's the acceleration due to gravity. But again, it's pretty much basic algebra from there. So these questions are pretty straightforward. Obviously, if you have questions as you're working on them, please ask. But I think you'll be fine. Okay, last one here, last example. A box has a weight of 160 newtons. What is the weight of a box on a planet where g equals 4.2 meters per second squared? Now you got to be careful here, because you really got to pay attention to what you're given and what you're looking for. In this case, we have the weight. It weighs 160 newtons. And we want to know what is the weight on some other planet where g equals 4.2 meters per second squared. So we have our equation, of course, W equals M times G, but we want to figure out the weight on this new weight here, right? So you might be tempted to say, oh, well, I'm just going to do 160 times 4.2. But that's not right, because 160 is not the mass. We need the mass right here. We don't have, the mass wasn't given to us. So how can we figure out the mass? Well, and I actually messed this up. On Earth is what the end of that sentence should say. Apologize. So this should rate a box's weight of 160 newtons on Earth. What is the weight of the box on a planet where g equals 4.2? So I'm sorry, that was a little confusing, but hopefully you see there has a weight of 160 on Earth. So if it weighs 160 on Earth, can we figure out its mass? Well, yeah, because we can use this equation on Earth, right? So this equation on Earth would be the weight was 160 equals this unknown mass, but on Earth we know what g is. It's 9.8. So I can figure out what its mass is from this right here, right? I simply would divide both sides by 9.8. Sorry, someone's leaf blowing outside. So 160 divided by 9.8, I get, for the mass, I get 16.33, I'm obviously rounding, kilograms. So then now, if I want to figure out what is the weight on this new planet where its g is 4.2 meters per second squared, now I can figure this out because I know the mass. So simply, the weight would be the mass, which is 16.33, times g, which is going to be on this new planet 4.2 meters per second squared. 16.33 times 4.2. I get 68.59 newtons. And you can do just a quick common sense check. Does that make sense? Obviously, Earth is 9.8 meters per second squared. So since this is smaller, that means this planet is smaller and has less gravity. So if it weighed 160 on Earth, it should weigh less. And that's what we see here. That it weighs only about 68.59 newtons. So once again, that would be the hardest of these types of problems. And it's not that hard. You just have to figure out the mass first. So you kind of have to work backwards, right? And again, I apologize, but this should say a box has a weight of 160 newtons on Earth. And then you're just finding it on this new planet. Okay, hopefully that made sense.